Hello everyone, welcome back to part two of the series on signal integrity. So let's begin. All right, so in the previous part, we discussed how to calculate this impedance at any location z as the ratio of v of z by I of z, and it is given by this expression, which is the characteristic impedance times the ratio of the voltage waveform to the current waveform. So now let us look at how we can use this expression to understand what is the effect of having an impedance at the load side. So consider this transmission line, and without loss of generality, we can assume that at the load side, so the transmission line is connected to a load ZL, and without loss of generality, we can assume that the place where ZL is connected is now going to be location 0. And looking back, it's gonna the Z is actually gonna go all the way to minus L. So the transmission line is still of length L, and characteristic impedance is Z naught. And obviously, this is the positive Z direction. So now we know that the impedance at any location Z is going to be V of Z by I of Z, which is this expression which was derived earlier. And then now at the location Z equals 0, we know that the impedance has to be ZL because at location Z equals 0, the impedance which is going to be the ZL, and therefore Z of 0 is going to, which is equal to ZL, is now going to be, if I substitute Z equals 0 in this expression, is going to be this expression. And now let us define V naught minus by V naught plus, which is the amplitude of the backward traveling wave, voltage wave, to the amplitude of the forward traveling voltage wave as some complex constant gamma. And gamma is, which is also known as the reflection coefficient. If we define V naught minus by V naught plus as gamma, then Z of 0, the impedance at location 0, which is going to be equal to ZL, is now going to be 1 plus gamma by 1 minus gamma times Z naught. Or if I write gamma in terms of Z naught and ZL, gamma is going to be ZL minus Z naught by ZL plus Z naught. So using this expression, we can now rewrite V of Z as V naught plus e power minus gamma Z plus gamma times V naught plus e power plus gamma Z. And similarly, the current can be written as this expression. So what we basically find here is that V naught minus by V naught plus, which is the ratio of the reflected voltage wave to the incident voltage wave, uh, which is also just the backward traveling voltage wave to the forward traveling voltage wave ratio, is equal to gamma. And so, if the load impedance ZL is different from the characteristic impedance of the transmission line Z naught, then this gamma is a non-zero quantity. So therefore, you are going to have some backward traveling wave for a given forward traveling wave, which means that the wave has actually reflected from the ZL Z naught interface. And here you see how this is mathematically represented. This is the forward traveling wave because you can see there's a minus gamma Z. So this wave travels along the plus Z direction. And the incident wave is now reflected by a factor gamma, and therefore this is the reflected wave, which is gamma times the incident wave. And similarly, you have the incident current wave, which is just going to be the incident voltage wave or Z naught, and the reflected current wave is going to be minus the incident voltage wave times gamma over Z naught. So thus, as I described earlier, if there is an so-called impedance mismatch, and therefore the load impedance is not equal to the characteristic impedance of the transmission line, then this coefficient gamma, the reflection coefficient, which is given by ZL minus Z naught by ZL plus Z naught, is going to be non-zero, which means it's going to have some complex value. And therefore, V naught minus, which is equal to gamma times V naught plus, is going to be non-zero, which means given a wave that is traveling along the plus Z direction, an incident wave with amplitude V naught plus, now you're going to have a reflected wave V naught minus of amplitude gamma V naught plus. Thus, there's going to be reflections. However, imagine a situation now which is so-called perfectly matched. If it's perfectly matched, then the load impedance is equal to the characteristic impedance of the transmission line. And under such conditions, the gamma is obviously going to be 0. And if the gamma is 0, then we find that the V naught minus is 0, and hence we get no reflected wave. What if, for example, you had an infinite load impedance? What does it mean? An infinite load impedance basically means that the load impedance, the load at the load side, the link is open. This is an open circuit condition. And therefore, if I substitute ZL equals infinity in the reflection equation, the gamma is going to be equal to 1, which means that V naught minus is going to be V naught plus, and I naught minus is going to be minus gamma times V naught plus over Z naught, which is going to be minus V naught plus over Z naught. So therefore, what's going to happen here is the reflected wave amplitude is equal to the incident wave amplitude, and therefore all the wave that was incident is now going to be reflected, and it's also going to be reflected in phase to the incident wave. But if you look at the current wave, you have a similar situation where there's some incident current wave, and almost all of the incident current wave is now reflected back. And this reflected back is also 180-degree out of phase. What if you had, so this case where there's an open circuit basically implies that, say you sent a 2-volt amplitude at incident wave, then the 2-volt amplitude incident wave is now going to reflect to create another wave which has an amplitude of 2 volts, but it's going to be in phase with the incident wave. So the total voltage at the output is now going to jump from 2 volt to 4 volt because of this reflection. So as we will discuss later, this reflection is going to cause issues now because it's going to cause basically these voltage fluctuations, depending on whether it constructively adds or destructively adds. What about if you had zero load impedance? The zero load impedance corresponds to a short circuit condition, and under this condition, ZL is 0, therefore gamma is -1. And in this case, V naught minus is going to be minus V naught plus, which means that all of the incident voltage wave is going to be reflected, but it's going to be reflected at 180-degree out of phase. So therefore, the incident wave and the reflected wave, because they're 180-degree out of phase, are now going to cancel out, and then the voltage at the load is now going to be 0, which makes sense because if it was a short circuit at the output, the voltage has to be 0 because the voltage across the short circuit is 0. And similarly, you have the reflected current waveform. So what we have learned, so to summarize till now, right, what we learned so far is, imagine you had a transmission line of characteristic impedance Z naught, and it was connected to a load impedance ZL. And if you assume that Z equals 0 corresponds to this load side interface between the transmission line Z naught and the load impedance ZL, then if we assume that V naught plus is the amplitude of the incident wave, then we are going to have a reflected wave with amplitude gamma V naught plus. And we are going to have a transmitted wave because some amount of the energy must be transmitted also. And the transmitted wave is just going to be some parameter t times V naught plus. But the transmission where t is also a complex number and called as the transmission coefficient. The reflected the current wave is just going to be gamma times the amplitude of the incident voltage wave over Z naught, as we've seen earlier. And obviously at the interface, because you're going to have two different impedances, the characteristic impedance of the transmission line, which is Z naught, and the load impedance ZL, at the interface, you can define this so-called complex reflection coefficient, which is ZL minus Z naught by ZL plus Z naught. This symbol here just means it's an element of the complex plane. So now what we can do is at this interface, so now we're going to try to understand what is the relation between the reflected wave, the incident wave, and the transmitted wave. What we are going to end up doing is, because of energy conservation, we are going to get a relation between the reflection coefficient and the transmission coefficient, which is going to be important for us to define certain concepts such as the insertion loss, the return loss, and so on. So at the interface, you're going to consider locally what happens, which means since the moment we go to this word locally, it means that we are going to consider at that location z equals 0. And within that location, obviously, the distances that we are going to consider are going to be much shorter compared to the shortest wavelength of the transmitted signal. And therefore, we can use a lumped element model. And hence, locally, KVL and KCL would apply. And so if we apply KVL at z equals 0, we get V naught plus the incident wave plus the reflected wave is going to be the transmitted wave. And similarly, you must also have continuity in current, which is KCL, which means that the incident current plus the incident current plus the reflected current must be equal to the transmitted current. So we use KVL and KCL. And if we simplify KVL and KCL, we get this situation that 1 plus the reflection coefficient must be equal to the transmission coefficient, and 1 minus the reflection coefficient must be equal to Z naught, which is characteristic impedance over ZL times the transmission coefficient. This expression here, 1 plus gamma equals T, is just a form of energy conservation because it says that the the total reflected wave and the total transmitted wave must add up to the total incident wave. And now what we can do here is these are basically two equations with two unknowns, the two unknowns being gamma and t, and you can combine these two equations to get a relation between gamma and t. Uh, sorry, we can combine these equations to basically determine what is t in terms of the z naught and zl, because we already know that what is gamma in terms of z naught and zl. So as you know, gamma is just zl minus z naught by zl plus z naught. And if you use these two equations, we find that the transmission coefficient is going to be 2 times ZL over ZL plus Z naught. So obviously, if the if the link at the Z equals 0 interface was perfectly matched, then you'll have a condition that ZL is equal to Z naught, and therefore the reflection coefficient gamma is going to be 0, but the transmission coefficient is going to be non-zero because all the incident wave is now going to be transmitted to the load. So considering from the signal integrity standpoint, this is exactly what we want. So we want to design a link in such a way that the link characteristic impedance is matched to the impedance at the load side so that minimal amount of the incident power is reflected and most of the incident power is transmitted to the load. Which is also, if you look at analogous to circuit theory, which is actually just doing maximum power transfer. Now let us look at time domain. So till now, all this was done in frequency domain because you remember the moment we start talking about j omega and impedances and all that, we're talking about how the behavior is with respect to one particular frequency. This is a frequency domain analysis. But now let's take a brief look into what this whole situation would look like if we were to analyze this from time domain, right? So, what would it look like in time domain? This also relates to something called TDR, called time domain reflectometry, because we're going to talk about how these waves are going to keep reflecting between interfaces and how they end up adding up. So let's try to understand this in a very simplistic way. So now you have this link. So you have this is a source, which is going to be some digital data, some digital signal, and then which has a source impedance. The transmission line, which, as we discussed earlier, is going to be along the z direction, going from z equals 0 to z equals L. The Vin is the input voltage at location 0 of the transmission line, and Vout is the output voltage at location L of the transmission line, which is connected to the load impedance ZL. So now what's going to happen? So imagine now, and we're going to also analyze this. We're going to consider only one frequency component now, because remember, if you use the broadband case and we have multiple frequency components, each frequency component is going to travel at a different speed, and therefore this analysis becomes extremely complicated. So we're going to consider just one frequency. That's why I've used one color here, the red color, to indicate it's one frequency. So you have the input at location 0, and you have the output, which is basically location L. So imagine now the signal starts from here, right? What's going to happen? The signal is obviously going to take some time to travel from location 0 to location L, because the signal has a certain finite time to travel along the length of the transmission line. And the velocity that the signal takes along the length of the transmission line is going to be basically the phase velocity of the wave, which is c over square root of epsilon effective. And if you remember from the first lecture on waveguides, we know how to calculate this epsilon effective. It depends on how the electromagnetic field distributes itself along the cross section of the transmission line. And it's going to be frequency dependent, because the frequency is going to determine how the mode is going to distribute in the cross section, as well as which modes are actually excited. So let's assume a certain mode is excited with a certain effective dielectric constant, and therefore having a certain speed, c over square root of epsilon effective. Then the time of flight, as it's called, which is the time it takes for the signal to go from the location 0 to the location L, is just going to be L over the speed, which is L over c over epsilon, square root of epsilon effective, which is called the time of flight. So now, what's going to happen is this wave is going to take some time TF to go from 0 to L. And then once it goes to L, obviously some of the wave is going to be reflected, some amount of the wave is going to be transmitted. And the reflected wave is also going to travel back now, taking the same time TF, and now it reaches back after a time 2TF, and so on. So now what happens is, after an interval of time, which is going to be 2 times the time of light, the reflected signal is going to go all the way back to the transmitted signal, and then it's going to add up at the transmitter side. So you end up having this so-called bounce diagram, which basically indicates how the signal is going to bounce at the transmitter side and the receiver side. So you have this incident signal that is going like this, it's going to reflect, transmit, and then this reflected signal is going to go all the way back to transmitter side. And because now there could be an impedance mismatch at the transmitter side also, because of Zs minus Z naught by Zs plus Z naught, some amount of the wave is going to be transmitted and reflected, and then this reflected wave is going to go again to the receiver side and is going to be transmitted and reflected, and so on. This in electronics, this is called bounce diagram, but if you go into the realm of physics, it's actually called a space-time diagram because it talks about how the electromagnetic wave is traveling through space and time. And obviously, we can define at each one of these interfaces, we can define what is the reflection coefficient, the transmission coefficient. So the reflection coefficient at the load side is going to be ZL minus Z naught by ZL plus Z naught. And the transmission coefficient at the load side is going to be 2ZL by ZL plus Z naught. While the reflection coefficient at the sender, which is the transmitter side, is going to be Zs minus Z naught by Zs plus Z naught. And the transmission coefficient at the transmitter side is going to be 2Zs by Zs plus Z naught. Initially, when imagine that there was a switch here and it was closed. Initially, what happens is, let's say the source started operating and the switch was closed. From the source side, it's basically going to see just this lumped element Zs. And this entire transmission line can just be treated as a lumped element Z naught connected to ground. And therefore, the input voltage is just going to basically resistively divide between the impedances Zs and Z naught. And then, therefore, the Vin at time t equals 0 is just going to be Z naught by Z naught plus Zs. This is just a voltage division times the applied voltage Vs. And this is the actual voltage wave at time t equals 0 at the location Vin that's going to now propagate along the length of the transmission line to reach V out. So what I'm basically trying to say here is, at the instant Vs was applied and the switch was closed, it's not going to see this entire length of transmission line, and it's just going to see the impedance Z naught as if it's a lumped element Z naught connected to ground, and therefore the voltage is going to divide between Z naught and Zs. And this divided voltage at the Vin is now going to propagate all the way to the other side to V out. It's going to get reflected, and over time, as the signal keeps bouncing back between the source side and the receiver side, the signal at the source side is going to build up and keep building up until ultimately the signal at the receiver side and the sender side is going to settle at the steady state value. So let's see what that looks like. So now I've added different terms to analyze the propagation of the wave. So the input wave is going to be Vn of 0. It goes all the way here at the receiver side. And as it travels, as we already know from wave phenomena, it's going to gain some phase, and the phase can be represented as some e power minus j theta. And obviously, this phase is going to depend upon the propagation constant of the signal along the link, which is beta, which we talked about in the lecture on waveguides. So it's going to be Vn of 0 times e power minus j theta. And there's a minus sign here because it's obviously a forward traveling wave. It's going to gain some phase. And now this some amount of the wave is going to be transmitted. So it's going to be this incident times TL. Reflected is going to be this incident times gamma L. And now this wave is now coming all the way here. And now what's going to happen? The wave, this is the incident wave. And now the transmitted wave is just going to be this times TS now because it's the source side. And then the reflected wave is going to be gamma S, gamma L times the original incident wave. And therefore, you can keep doing this and you see how it gets more and more complicated because now you have to, at each interface, now you're going to have to multiply the corresponding gamma L or gamma S, depending on whether it's being reflected at the load side or the receiver side. And similarly, you need to multiply by TL or TS, depending on whether it's transmitting, whether it is being transmitted to the load side or the receiver side. And now what happens is you have all these voltage waves being bouncing back, bouncing between the source side and the load side. And therefore, at any given time, that is, say you're now looking at time steps. So you're looking at 0, TF, 2 TF, 3 TF, etc., where TF is the time of flight. And therefore, in order to know what is the voltage at any instant of time, say T, we need to just add all the voltages that we would get. We would get, right? So because initially the voltage was Vn of 0, and now you need to add to it this voltage wave, which is basically gamma times Vn of 0 e power minus 2 theta minus j2 theta. And you need to keep adding all of them to determine what is the voltage at, say, the source side, and similarly add all the terms to get the voltage at the receiver side. So also we can do this at any location z. So for example, we can choose a given location and then say z equals L over 4. And at this location, if you want, at this location, if you want to know at any given instant what is the voltage, you just basically find out what were the various voltages that reached that point, and then that would, you need to add them up to get the overall voltage at the location z equals L over 4. So now let's look at diagrammatically what that looks like. What is the result of the bounce diagram? So initially, oh yeah, sorry. This is the voltage that is plotted at location L over 4 at a given time. So this is the location L over 4. And I'm going to now see with time how this voltage at location L over 4 is actually building up. So initially, if you notice, the when the at time t equals 0, when the voltage at Vn was Vn of 0, the voltage at the location L over 4 must be 0 because the signal here has not reached there. But after a certain time here, which is the time it takes for the signal to travel this distance L over 4, which is just going to be TF over 4, the signal is first going to start, we are first going to see the signal. And then after every bounce and then coming back to this location, the signal is going to keep adding up. So that's what is indicated here. So at time t equals 0, the signal at location L over 4 is 0 because no signal has reached there. And once the time is t over 4, the signal has suddenly built up to Vn of 0. Because remember, Vn of 0 was the one that's traveling here and finally reaches L over 4 at time t over 4. The capital T here is just time of flight, TF, that was written in the earlier diagram. And so at time t over 4, the voltage now jumps to Vn of 0. And then every time the signal reaches back at that L over 4, you just keep adding the signal that was received to get the actual total signal at that location L over 4. So you see how the signal, which was originally 0, is slowly going to build up as we keep adding all the reflections. And over time, the signal is finally going to settle at its steady state value, right? So and this expression for calculating this voltage can get quite complicated, as you can see here. And here we also understand how the transmission line model differs with respect to the lumped element model. If this was a lumped element model, the moment you close the switch, the location at L over 4 will immediately see the signal. But because of the finite time of flight between the source side and the receiver side, and because of the reflections, you see that the signal at the location L over 4 is not going to instantaneously go to the final value, but it's going to take some finite amount of time to reach its final value. And this is a reason why these reflections can basically lead to various kinds of signal integrity issues. So now that we talked a little bit about the time domain analysis and how these reflections actually look like in a time domain, let's go back to our frequency domain analysis to now come up with the concept of insertion loss and return loss. Yeah, we can take a 1-minute break here. So let us go back here now. So what we have learned so far, there's a transmission line with a characteristic impedance Z0. And at the interface at Z equals 0, there's basically a load impedance ZL connected, right? Incident wave is going to be V0 plus. Reflected wave is going to be the reflection coefficient times the incident wave. And the transmitted wave is going to be the transmission coefficient times the incident wave. And these are the reflection coefficients and the transmission coefficients that were calculated earlier. Till now, we have completely just talked about voltages, but to get an understanding in terms of energy or in terms of power, we can now start talking about the concept of insertion loss and return loss. So now if we talk about power, and in this case, we mainly care about the real power because the real power is the actual power that's going to do work, and that's the power we want to successfully transmit to the receiver from the transmitter. So the real power, as you know, power is a complex quantity because the voltages and currents are complex quantity, and power is just V times I. So the complex power S can be written as a real part and an imaginary part. Because the complex power S is defined as the complex voltage times the complex current complex conjugate. And therefore, the real power is just going to be the real part of the complex power. So it's going to be the real part of VI complex conjugate. Now we are going to consider what happens how the power is going to divide at the interface. So at the interface, the incident real power is just going to be, using this expression, real part of. What is the incident wave? Remember, the phase factors here, the e power gamma z and minus gamma z, are going to go away because we are assuming that at the interface z equals 0. So if you put z equals 0, the phase factors are just going to disappear. And therefore, the incident real power is just going to be a real part of the incident voltage, V naught plus, times the reflected current. Sorry. The incident real power is going to be the real part of the incident voltage times the incident current complex conjugate. So it's going to be V naught plus times V naught plus complex conjugate over Z naught complex conjugate. Similarly, the reflected power can be defined as a real part of the reflected voltage wave, which is gamma times V naught plus, times the reflected current, which is minus gamma V naught plus over Z naught complex conjugate. Similarly, we can also write the transmitted real power as a real part of the transmitted voltage wave, which is T V naught plus times the transmitted current, which is T V naught plus over ZL complex conjugate. Notice here, and this is very important, that for the incident wave and the reflected wave, to determine the current, we had divided by the characteristic impedance Z naught. But for the transmitted wave, to get the current, we had divided by ZL. Because remember, for the transmitted wave is now going to this region which has an impedance ZL, and therefore you have to divide by ZL to get the current, and not Z naught, because Z naught was actually located at Z equals 0 minus, not Z equals 0 plus. So if you now simplify these expressions, we find that the incident real power is just going to be V naught plus mod square over Z naught. And how does the mod come? Because remember, V naught plus times V naught plus complex conjugate is just going to be mod V naught plus square. Because when you take a complex number and multiply it by its conjugate, it's just going to be mod square of that complex number, right? So you're going to have, and we're also going to make one more assumption, which is in general, for most cases that we consider, and also for real cases, the transmission line is going to have a real impedance, or you want to design the transmission line to have a real impedance because we want the voltage and current waveforms to be in phase with each other. Therefore, Z naught complex conjugate is also Z naught. And if we use this, we get the fact that at the interface, the incident real power is V naught plus mod square over Z naught. The reflected power is going to be the incident power, but times mod gamma square. And the transmitted power is going to be the incident is going to be mod T square, V naught plus square over the load impedance complex conjugate. Notice here that the load impedance over here, notice that the load impedance here can be complex. So the transmitted real power you have to take the real part of this value because the transmitted load impedance can be complex. So now what you can do is, let us now talk about what actually happens. So let's talk about the concept of incident power, reflected power, and transmitted power. So the incident power we calculated earlier, and when we talk about power, we always care only about the real part of the complex power or the real power. So the incident power, as we calculated earlier, is going to be V naught plus over Z naught. This is a reflected power, and this is a transmitted power. And rather than just representing the values of these powers, it's more useful to create a comparison between the powers. So what we can do is we can create a comparison between the reflected to the incident power and the transmitted to the incident power. And that comparison will get a better understanding of what actually happens when the incident wave either reflects or transmits and so on. So how do we typically create a comparison between power? We create a ratio of the reflected or the transmitted power with respect to the incident power. And because the transmitted and reflected power can sometimes be very, very different from the incident power, it's good to represent them in a log scale or in a dB scale. So what we are going to do now is we are going to say that the return loss is just going to be 10 times log to the base 10 of the reflected power or the incident power, and the insertion loss is going to be 10 times log to the base 10 of the transmitted power over the incident power. So what this is basically saying is it's creating a comparison between how much power is reflected and versus incident, or how much power is transmitted versus incident in the log scale or in the dB scale. So if we basically substitute the values of powers calculated earlier, the return loss is going to be 20 log to the base 10 of mod gamma, and the insertion loss is going to be 20 log to the base 10 mod t plus 10 log to the base 10 of z naught by zl's complex conjugate. And here you have the restrictions on the value. So gamma must be a number, mod gamma must be a number between 0 and 1, because energy has to be conserved, and therefore log to the base 10 of gamma is some number between minus infinity and 0, right? Remember, since mod gamma is a number between 0 and 1, if you take the log of a number between 0 and 1, the range of that quantity must be between minus infinity and 0. So therefore, what ends up happening is the return loss is going to be basically negative, and the best return loss you can have is basically the worst return loss you're going to have is basically going to be 0 dB. Similarly, for the insertion loss, you can define this. And again, because the transmission coefficient, the mod of the transmission coefficient is also a number between 0 and 1 because of energy conservation, therefore log to the ben of the mod of t is also going to be somewhere between minus infinity and 0. So now let's look at how the insertion loss and the return loss of a given link or of a given transmission line with some load connected at the receiver side is going to behave when the transmission line is matched to the load versus when the transmission line is not matched to the load. So remember before I talked about this fact that gamma is a number between 0 and 1. So imagine now the transmission line was perfectly matched to the load. So if it's perfectly matched to the load, obviously gamma is going to be 0. And therefore, as gamma is going to be 0, then you have a situation where log to the base 10 of gamma is going to go towards minus infinity, right? And similarly, for a matched Z naught to ZL, the transmission coefficient is going to be close to 1 because almost all the signal is now transmitted, and therefore log to the base 10 of t is going to be much closer to 0 dB. So for a matched network, you have the situation where gamma is going to be a very small negative value. It's going to be, sorry, a very large negative value. It's going to be more towards minus infinity, while mod t is going to be more closer to 0 dB, right? So if you plot in a dB scale, this is what a matched link would look like. You see that the insertion loss is close to 0 dB, but there would be some decay with frequency because as the frequency increases, because of a certain phenomenon called skin effect we'll see later, the loss in the transmission line increases with frequency. So it's going to be very close to 0 dB, but it's going to have some degree of decay in the insertion loss with frequency. The return loss, remember, is going to be a large negative value. So it's going to be some negative value, which is going to be here, maybe say, for example, minus 60 dB. It's not going to be minus infinity because you can have it's not possible to have no reflections. So it's going to be some large negative dB value. And generally, in practice, if this large negative value is less than minus 10 dB, we typically say that the link has been matched. This concept is also applicable to antennas because if you remember, if you had studied antennas, you know that when you have a transmission line connecting to an antenna, if the antenna return loss is less than minus 10 dB, you say that the antenna is a good antenna because it's a good radiator. Why we say that? Because in the antenna design case, it's very similar to the case we talked about here, but there the load impedance is now going to be free space, and therefore you need to match the characteristic impedance of the transmission line to the impedance of free space, which is going to be around 377 ohms, which is root mu naught over epsilon naught, basically, for free space. So this is what happens when the link is perfectly matched. This is what the insertion loss and return loss would look like. Now let's imagine a situation where the insertion loss and the return loss had some frequency dependence. That is, they are matched only within a certain frequency range, but out of the frequency range, they are mismatched. So this is a band pass case. So imagine that they are matched at about a frequency f naught, and within a certain bandwidth about that frequency f naught, they are perfectly matched. But anywhere beyond that bandwidth, they are mismatched. So how would this look like? So remember, insertion loss close to 0 dB means it is matched. But here, it's only matched within this frequency band. So away from it, you're going to have a large negative value of insertion loss in dB, which means that less of the signal is transmitted. And near this central frequency f naught and above its bandwidth, the insertion loss is now going to start going towards 0, which means it's getting matched, and therefore more signal is being transmitted towards the load. And similarly, if you look at the return loss, it's going to look something like this, where it's going to be closer to 0 dB, far away from the center frequency, which means that most of the signal is now being reflected. But as we go towards the central frequency about its bandwidth, a large amount of the signal is now transmitted and less is reflected, and therefore it's going to go to a large negative value, which means it's now going to drop within this frequency band to less than minus 10 dB, which means within this frequency range, it is now matched. So usually what we can do is for this particular kind of link, we would say that the link behaves as a bandpass filter because it lets the signals pass about a certain central frequency, and it has a certain bandwidth within which the signals are basically transmitted and less amount of them are reflected. So before we go on to the next concept, which requires a little bit of understanding of complex analysis, I'm going to take a break, and we're going to talk about this in part 3 of the lecture series. Thank you.